lecturer in physics. Now, it's a treat in store because this year we are celebrating the anniversary of the discovery of the laser in 1960, and David Jamieson is going to talk to us, and the only advice I have to give you is what I saw at MIT in the second year lab. Don't look into the beam with your remaining eye. David Jamieson, apart from being head of physics here, is also a luminary in the sort of aspects of physics that he'll tell you about.
Well, Tony, thank you very much for that introduction. As Tony mentioned, this year we're celebrating the 50th anniversary of the laser in the July lecture program, so I'm kicking it off tonight. But please, if you're interested, please come back and join us for the next 3 Fridays in July, where we'll explore lasers in astronomy, lasers on biomolecules, and of course the solid-state laser, which enables the great complexity of our Western civilization. Please note that in some of our flyers we said parking on the campus was $5. I'm sorry, it's gone up to $7. My apologies for that oversight. Okay, so tonight, the history, the invention, the great invention that we're celebrating. I want to start right back at the beginning, and always with modern physics, Einstein had a hand in it. And I want to try and explain to you how the laser works. I've got some real lasers up here on the stage, including an extremely powerful one which lives under there. We'll see if we can get that out, and I wouldn't like to be one of those balloons towards the end. But first of all, I just want to briefly revisit my July lecture from last year. Can I just ask for a show of hands, how many people were here at the July lecture last year? Okay. Oh, great, thanks. So our very active press office put out a press release on that July lecture highlighting the idea that Galileo may have discovered Neptune, and she put it out in Australia, and the only person who took any notice was Red Simons, and I got 10 minutes with Red on his morning show. And nobody else took any notice whatsoever. And she said, oh no, it's an entertaining story, we'll put it out internationally. And I said, well, don't waste your time, no one's interested. She said, no, trust me. So she put it out, she rang me up and said, I've just released it onto the wire service. 5 minutes later, my email inbox exploded. And now, if you Google up Jamieson Galileo, you'll find 10,000, 20,000 hits, including the calls for the Vatican to release the suppressed Galileo Codex that Jamieson has discovered and get this whole affair out of the open. But it did lead me eventually in April of this year on one of the most profound experiences of my life as a physicist, which was to the National Library of Florence, organised by my colleagues in the School of Physics at the University of Florence, where I got to spend 2 hours with Galileo's original handwritten astronomical notebooks from the great discoveries of 1609, which we were celebrating 400th anniversary of last year. And here's me studying with my specially made magnifying glass for the occasion, his observations of Neptune from those magic nights of December 1612 and January 1613. On the published data on this book, there's a missing week of observations when Neptune would have done a retrograde loop through his telescope. I found the missing page. Anyway, this story is not yet finished, but that's not the story of tonight's lecture. But on the astronomical theme, I want to start tonight's lecture on Mars. This is the view over Gusev crater. When the sun rises on Mars, it's always a beautiful day because there's very few clouds, not much water, apart from when there's a dust storm. The sun's light shines down on the Martian atmosphere, and the energy of the sunlight is absorbed in the thin gases of the outer atmosphere, predominantly carbon dioxide. Now, there's a curious quirk of the carbon dioxide molecule. It's a molecule, of course, much beloved of the citizens of Victoria, because no one outdoes us in producing carbon dioxide. The per unit of energy generated. But this peculiar quirk means that some of the sun's energy is absorbed and not released. And these carbon dioxide molecules build up in this excited layer, and then one of them decays, and that photon shoots through the layer of excited carbon dioxide, triggering a photon avalanche. Indeed, this is a laser in the outer atmosphere of Mars that was discovered back in the 80s, a naturally occurring carbon dioxide laser in the atmosphere of Mars. So this is a remarkable phenomenon. It's time to drill down and learn more about it. Now, the laser was invented by humanity long before it was discovered in a scientific laboratory. It's remarkable how well primed we were before a laser actually came on the scene. It's almost as if humanity pulled the laser into existence to satisfy its expectations, because if we look at the popular history of the laser, it goes way back. It starts perhaps in 1898 with H.G. Wells, who unmistakably describes an infrared laser from the attacking Martians in this War of the Worlds. And he even describes some of the details of the furnace and the mirrors that generate this ray that are very resonant, very reminiscent of the resonant cavity that we need to make a laser. Then if we step forward, this actually I have to say is a book from my own personal collection. I don't recommend this to you for the storyline, but in this story, which was written in 1933 by Otis Klein, there is nevertheless a very accurate description of a green visible laser that was invented by, yes, the little green men of Mars. When I first read this book, when I was very much younger than I am now, by many decades, I always wondered why the little green men would still use swords when they had what was unmistakably a laser weapon that you could use. So anyway, but it wouldn't have made such a great story, I guess. But then we jump forward. The laser, by 1974, of course, had been well invented. Larry Niven is a great science fiction writer, and he incorporated a very powerful laser into this story, A Mote in God's Eye, which I recommend to you. This is worth reading for the story, where this yellow star has a number of has a civilization around it that is penned up on its home planet for various technological reasons. And a remote observer one day observes the star goes red and stays red for a number of decades, and then switches off and goes back to its original colour. So the yellow star is the mote, and this is the constellation of the god, hence the mote in God's eye of the title. But what the people who were observing this didn't know, this laser was being used to propel an interstellar probe. By the way, did you notice the colour of the background of the slide just changed there? So whenever you see the background colour is this salmon pink, it means what's on the slide isn't true. Okay? Now when it changes to green, it's back, it's true again. Right? Just in case I need to make a few excursions during the lecture. The Planetary Society, of which I'm a member, is about to launch a second attempt, a solar sail which will be propelled through space by the pressure of sunlight. And of course what Niven was anticipating, that one day you could leave your photon engine on Earth and direct the laser beam at a solar sail and push it through space, possibly on an interstellar journey. Because after all, you don't have to take the engine with you. It's a very good way of doing business. Then we step forward. Oh, and I should have mentioned, I had the pleasure of meeting Larry Niven in person when I was a Caltech postdoc back in the mid-80s. He's not such a great guy to talk to face-to-face, of course. Let us jump forward to 1964 here. This is remarkable because this is only a few years after the laser was real. Nevertheless, it still gets a pink background because this is James Bond in the film Goldfinger. And we're going to have occasion to look back at what's happening here. Obviously, James is in for a very nasty experience because that's unmistakably an extremely high-power ruby laser there, and it's heading in a direction which is unfavourable. So we'll come back to that one later on. Obviously the laser is huge in popular culture. And finally, in my survey of the laser, the popular history of the laser, I'd recommend this book to you. It's science fiction, of course, but it's dignified because it got written up in the journal Nature, which is one of the most prestigious journals in science. And in this remarkable parallel universe story, theoretical physicists are incarcerated in monasteries and aren't allowed contact with the outside world because they do potentially undesirable things on this particular planet, and they're not allowed to get access to high technology. However, during a crisis, an orbiting spacecraft is discovered which shines a laser down on some of these monasteries where the theoretical physicists are incarcerated, and they have a spectrograph and they measure the frequency of this laser and its attributes, and they realise it can't have been generated from electrons jumping up and down between energy levels of atoms found on that world or anywhere else in that universe. It's a rollicking yarn, and the physics, of course, are somewhat implausible, but nevertheless enormously entertaining, and it did get written up in Nature. Finally, I noticed that this guy, Banksy, is all the rage these days, and of course Banksy is not immune from popular culture, well indeed is perhaps central to popular culture, and I would note this exhibition in Bristol where the wildly familiar green ray that the aliens always seem to have features prominently in his art. Yes. Sorry, I don't know how that got in. Okay, so laser fundamentals. To start, ladies and gentlemen, there are plenty of seats right down the front if you don't mind training and a little bit of laser light, and there are a few isolated seats here and there. First of all, I just want to start with the electromagnetic spectrum because the laser is all about light, light amplification by stimulated emission of radiation. So I want to just mention that the visible spectrum of light covers light of many wavelengths. The wavelength is the distance between successive peaks in the electric field that is associated with light propagating through space at the speed of light. And the visible spectrum spans wavelengths from about 400 nanometers all the way up to 750 nanometers. On this scale, a human hair would hardly show a curvature. These are very tiny numbers. Tiny, but nevertheless readily measurable. And so we're going to have occasion to talk about lasers across this spectrum, including a few that are off to the right, therefore couldn't be called lasers because they don't involve light, but they involve longer wavelengths of radiation, particularly microwaves. Now, I first encountered the idea of a laser outside of the literature, which I previewed at the beginning of the lecture, with this article in the Scientific American, the Amateur Scientist column, which I read in 1974, which had an intoxicating vision of a laser you could make yourself. And the beautiful drawings in this article made it plausible that I could actually make this myself, and I did indeed begin to accumulate the parts. If we zoom in at what's involved here, these are the basic elements of a laser. We see we've got a tube here into which one admits gas, and this gas, chosen carefully, is the lasing medium, the place where the light is produced. And this box is threaded with these two sheets of copper which are connected to this large capacitor with an induction coil and a high voltage power supply. And by switching this on, you can make the electric currents and the charge in this capacitor flow backwards and forwards, so you get quite a vigorous electrical discharge inside the gas, into which you inject energy into the gas. And as that energy dissipates, it produces light. Well, in this case, it produces ultraviolet light with a wavelength of 337 nanometers, invisible, which is then emitted from the windows at the end of the tube. Now, I got these images off the compact disc, which is a compilation of all the amateur scientist articles for the past 40, 50, 60 years. And being a modern compact disc, it's got a safety rating of each of the projects. And because this produces quite a powerful, invisible, ultraviolet beam of radiation with a pulse power of between 50 and 100 kilowatts, the safety rating on this one is off scale. Do not build this. But it nevertheless showed that these things didn't necessarily have to be very complicated. So let me start, Steve, could you fire this one up for me? So let me just start with the basic physics. If you have a piece of hot metal, such as the tungsten filaments in the lights in this lecture theatre, or indeed the tungsten filament in the light of this projector, and you pass that light through a, what have we got, a diffraction grating here, and, you can see it produces a continuous visible spectrum. Now this is what, of light, and this is what always happens when you have light vigorously interacting with matter. It will, as you inject the energy, in this case by the flow of electricity, you heat up the filament, you're injecting energy into it with particular power, and that spreads itself out by electrons bouncing around inside the hot filament, and they rearrange themselves in such a way that they radiate a continuous spectrum, more particularly called a black body spectrum. Now, I've just got, before I fire up the Bunsen burner there, I thought I would just show you this, because this is my attempt to explain this to my children about 15 years ago. I made them this toy, which is an illustration of the rearranging that goes on when you inject energy into a system and you get this continuous distribution of energies that we see in the continuous spectrum there. So let's put a number of electrons into this model at a high energy, represented by the height they are above the bench here. And then by pulling the trigger here, we can release them and have them interact with the atoms in the solid represented by all these pegs. And you can see that some of them will go fast, some of them will go slow, and they'll change around all the time. And some of them get stuck. We can take that one step further. Well, maybe I'll do it again with the red marbles. And if you look closely, you can see there's quite a difference in arrival times of the marbles down the bottom. So some got there very quickly, they're the high energy parts of the spectrum, the blue end of the spectrum up here, and some went more slowly, that's the red end. But this is a smooth and continuous distribution, as reflected by the fact that the rainbow is smooth and continuous as well. But the real world is not smooth and continuous. Fire it up, please. Quantum mechanics intrudes. And so if we now put in the path of this beam of white light, with this smooth and continuous distribution, a lump of matter, and we persuade the vapour of this lump of matter to enter this path. Oops, what have I done? What are those two horizontal lines? Got some on the lens. Okay, so you'll notice what's happening now as the vapour from the lump of matter here goes into the path of the beam. You can see a single dark line, point it out again for us, Steve, appear in the yellow part of the spectrum. And indeed, this is a lump of salt, and by spraying water on it, I'm vaporising the salt, and this is sodium vapour, which is absorbing in the yellow part of the spectrum. But something's different about the way the sodium interacts with the light, because it's only got a single line, or more particularly, if you look at that up close, you'll see it's a pair of closely spaced lines. Whoops, and I've completely overdone it. All right, we might call a halt on that one. Oh, look. So when you turn off the white light, you can now see the other side of the sodium atom, that when those sodium atoms which were previously absorbing the yellow light and leaving a black stripe in the spectrum are now emitting the yellow light, and we can see the emission spectrum because we've turned off the very bright light from the projector. We can see that's an emission spectrum of a single yellow line, this apparatus. And when it's an absorption, it's a dark line. So we see quantum mechanics here. We see a discrete behaviour. Thanks, Steve. That's great. So we need to understand this quantum behaviour for the purposes of understanding a laser. We also need to understand what's going on inside the sodium atoms here and in atoms in general. Here's a sort of semi-quantum model of an atom. We've got a nucleus in the middle here, and we've got electrons orbiting around the nucleus. And these electrons orbit in such a way that they actually lose their identity as a particle, and they smear themselves out in the form of a wave around the nucleus. And only waves that have an integral number of wavelengths are acceptable to the electron. And if for some reason it was forced to occupy some intermediate position in which it didn't fit a nice integral number of waves, it would rearrange itself promptly until it settles down into one of these nice orbits. And for that reason, an electron, although it's pulled very strongly by the positive charge of the nucleus acting on the negative charge of the electron, it won't fall in, because you can't fit a wave of the right number of wavelengths in the nucleus. So fortunately, all the atoms in our bodies don't collapse onto themselves. But electrons can jump up and down between the energy levels, and when they do, they fall down, they emit a photon. If they get lifted up, they need a photon of light to do that. So here's my simplified model of an atom with only two energy levels, a ground state and an excited state. If a photon comes in, it can excite the electron, and then later on the electron will decay and emit the photon back again. And they're very choosy. This can only happen if the photon energy is exactly right, and it's a very sharp colour. And you saw in the example of sodium, you could see just how sharp it was. It wasn't a fuzzy line, it was quite a sharp line. The atoms are very choosy about which electrons they absorb. Now, that's the situation as it was until Einstein came on the scene. And Einstein wanted to study this process of absorbing and emitting light by atoms in more detail. And so he said, let's see, I can think of two ways a photon can interact with an atom. The first way is whether if the electron in the atom absorbs a photon and is lifted to a higher state. The photon disappears, the electron is lifted. Another possible way is spontaneous emission, where an electron in an excited state sees an opportunity to decay, falls to the ground state, and emits the photon back again. But Einstein realised that the laws of quantum mechanics allowed a third way of interacting with atoms, and that is stimulated emission. If you take an atom which for some reason is stuck in an excited state, and a photon of the right energy for this transition comes past, the electron won't absorb it because it's already in its excited state, but indeed the photon will trigger the decay. So where there was one photon, after it's gone past this excited atom, there are now two photons, and they are identical. The two photons are locked in synchronization with each other because the first photon created the second photon through the medium of the atom. Now, that's it. That's what a laser is. Stimulated emission. Einstein did all the maths back in 1917. So you've got to ask, why weren't lasers invented in the 1920s? This is my artist's impression of an Art Deco green laser pointer. I downloaded this image from the Flashlight Museum website. I'm not making this up. The basic recipe is to pump lots of atoms into that excited state and hope they stay there long enough, so you get a lot of them up there, and then wait for one of them to decay. This will stimulate manipulate all the rest, and voila, you get this laser beam come out. But the reason why this wasn't invented in the 1920s is because there was very little electronics in the 1920s. What there was just emerging into the vacuum tube era. There was no theory of semiconductors, which is what you need to make the really good lasers, and the basic spectroscopy of studying the atomic properties and the molecular properties was poorly developed. However, I would present to you, ladies and gentlemen, this evidence that people were thinking about it from our very own city of Melbourne. This is the mural by Napier Waller down on Newspaper House in Collins Street, the girdle around the world. And we see this character here in the middle is doing something interesting. First of all, he's clearly blowing on a vuvuzela. So possibly there was a soccer match going on somewhere at the time. But you'll notice that this vuvuzela is being used to produce coherent radiation. And this is 1933. So possibly lasers did exist then. And of course, you notice the colour has changed. There's this genre called steampunk. You see, I had to dig really deep to get the information for this lecture for you tonight. This is what one might have looked like in the pre-electrical era. Anyway, we'll move on. Now, let's get back to the real history. I want to introduce this remarkable molecule, the ammonia molecule. It consists of a nitrogen atom with 3 hydrogens. And this molecule is deceptive in its simplicity because this whole thing can be set vibrating and wobbling. And every now and then, the nitrogen atom will tunnel, in the quantum mechanical sense, through the plane of the 3 hydrogen atoms and turn the whole thing inside out. This is called the umbrella inversion. This is a quantum mechanical process for which there is no classical explanation. The nitrogen atom tunnels through space to turn the molecule inside out. There are lots of ways of this molecule interacting with electromagnetic radiation. It doesn't interact very much with light, but in the microwave region, the microwaves can hit this molecule and set it vibrating in all sorts of ways. Now, I have to take my coat off for the next bit because there's a lot of heat. There was an expert at the University of Columbia called Charles Townes who'd spent much of his research career studying the way microwaves interacted with this ammonia molecule. He knew about Einstein's ideas of stimulated emission. And so, to put energy into this molecule, he decided to irradiate it with microwaves and see what happened. He was looking to create a microwave amplifier. This is not a laser, because laser is light amplification by stimulated emission of radiation. But the rest of the physics world was hot on the trail of trying to do the same thing. And so much heat and light was generated by all the adversaries working in the competing projects that eventually it worked. So here we have the 3 adversaries putting heat and light into the project. First, I mentioned Charles Townes at Columbia University. He was also a consultant at Bell Labs, the telephone company research labs. His claim to fame is that he invented the maser, the microwave amplification by the stimulated emission of radiation, had ideas for what he called an optical maser, which is a silly name because that would be the optical microwave amplification by the stimulated emission of radiation. And he worked in an East Coast USA university. Prestige. He got it working. He developed a stimulated microwave emission maser using the ammonia molecule, for which he went on to win the 1964 Nobel Prize. Now, he had briefly a PhD student called Gordon Gould, an unusual sort of guy. Unfortunately, I can't give you the details of his private life because this is supposed to be a family lecture. But he worked for Townes as a student for a few years, didn't finish his PhD, and he was obsessed with the idea of a laser. And in fact, he invented, his claim to fame was that he invented the name laser and had lots and lots of ideas of how to make it work. But he didn't make it work. Partly because after he left Columbia University, he joined this research company that got a $1 million grant from the government, the US government, to make a laser. But he, because of the aforesaid details of his private life, he couldn't get a security pass to work on his own research project. And so this was very difficult. And even an affair with the head of security didn't want to go. But because he got the local chemist to sign his notebook when he wrote the word laser for the first time and sketched a few ideas, he was able to fight Towns, the other guy here, and the rest of the country about the patent priorities of the idea, and it went on for more than 20 years until he finally won the patent battle and began to collect royalties on the laser. The laser community were not happy about this. And the final adversary is Theodore Maiman, who in 1960 did indeed get a laser to work with light, not with microwaves, for the first time, and that's the anniversary we're celebrating this year. So his claim to fame was he invented and demonstrated the first laser, and it was based on a crystal. But his handicap was that he worked for Hughes Research Labs, which was an aircraft research lab, and it was on the west coast of the United States. And in the 50s and the 60s, all the science was done on the east coast. So people pretty much ignored him. So I've read the 3 books that these guys wrote about their discoveries, and it's like a science fiction story, because these 3 books are set in 3 parallel universes. And the aliens are the other 2 guys here, depending on which permutation and combination. There was a lot of adversarial going backwards and forwards. But let me describe the breakthrough that Towns made that led to the laser. So we'll talk about the microwave amplifier. Towns recognised that there was a missing ingredient in Einstein's stimulated emission. He recognised that if you just had a 2-level system, you could create a photon when it decays, but that same photon would lift the atom straight back up again, whereupon it would fall straight back down again, and you couldn't get any gain, any amplification. He recognised, though, that if you allowed the electron, the excited electron, to take a sideways detour into a vibrational mode of the ammonia molecule that lived for a lengthy period of time by molecular standards, a few microseconds maybe, then you could create the required, you could pump the electrons up and have them stay there. So this is a detour of the decay via a metastable state, and you notice that when it decayed, it emitted a red or a lower energy photon compared to the yellow photon, the higher energy photon that was emitted via the direct route. That's important. So here's Towns' basic idea. You take a whole pile of ammonia molecules that can be in a ground state, an excited state, or this little side state here, the detour. You fire in energy. In this case, he used an electrical discharge, and you get them all excited into this temporary little level. And then further yellow photons coming in will not stimulate the emission of any more radiation. The system will stay there until it's triggered by a red photon in this example, which will create 1, 2, 3 additional photons. So here we have the amplification effect. The red photon is amplified by a factor of 3 in this example. Now, I have a toy for that too. So, this is the idea. You take a system in which there's an excited state and a ground state. It's making me very thirsty. Anyway, if you don't have a sideways detour, everything just falls down straight away. However, if you do put in a sideways detour, represented by this extra little energy level here, things slow down. It's acceptable to have a little bit of infrared. So that level is there to unhold it. Or indeed, you could have something like this. It lives for a very long time. Until, oops, remember to cut first. Oh, it releases its stored energy with an enormous thunderclap. And indeed, we'll get to an example of that sort of laser. Sort of thing hadn't decayed. And that could provide a very powerful amplification indeed. So here is the gadget as it worked in the laboratories at Columbia University. There's Towns, he's the boss. There is Jim Gordon, his student, who worked on getting this up and running. This is the maser. These are tubes through which excited ammonia are introduced. There's normally a window over here, and there are powerful vacuum pumps to prevent the ammonia colliding with air molecules and de-exciting prematurely. And this created a sensation, because this was the first way radiation could be amplified using the stimulated emission idea. Now, I have from Jim Gordon's memoirs a photograph that was taken a few minutes earlier. I'll get to that in a minute. This was named, with great ceremony, the Masertron. And that name lasted for approximately 5 minutes until Towns said, "We're not having any names with tron in them," and hence it became the Maser. Now, you've got to have good students working on your projects to make these things work. I mean, this guy got the Nobel Prize, and this is the photo taken 5 minutes earlier. Gordon cleaned the lab up for the publicity photo. Anyway, this did go on to win Towns the Nobel Prize, and remarkably, there were 2 Russians working mainly in theory in parallel, because the whole community was very interested in having this work, who shared the Nobel Prize in 1964. This is of note because Prokhorov here was actually born in Australia, in Atherton in Queensland. His parents had escaped the, I think, the revolution and took refuge in Australia, and when it was safe to go back, they returned when Prokhorov was only 7 years old. I think it's a bit rich to call him an Australian Nobel laureate, but I'm willing to do it. Anyway, so much for the maser. Microwaves. Very good for doing astronomy and for possibly for communications, although it has to be said that when Towns went down to the Bell Labs patent office and said, "Look, I've just invented the maser, it amplifies microwaves, and here I've got some ideas where we can extend that into the visible spectrum and make an optical maser," that was his name for it, "which could amplify light, and this might have applications." And the patent attorney at Bell Labs said, look, Charles, we're a telephone company. We don't do optical communications. Get out of here. So Towns went out, went and found another patent attorney elsewhere in the organisation and did get a patent on it. Otherwise, he wouldn't have spent 25 years fighting with Gordon Gould about it. So Bell Labs did eventually patent the maser. So much for microwaves. What about light? Well, it turns out light is much more difficult to create the necessary metastable state. And when you look at the literature from the late 50s after the maser was announced, there was huge activity. People studied all sorts of materials, trying to find something with the right properties to make a laser instead of a maser. Towns was very keen on vapours of alkali metals as the lasing medium. Also noble gases in glass boxes. Chromium-doped sapphire and phosphorus-doped silicon were all prime candidates. The one that won was chromium-doped sapphire. But let's just take a detour through the phosphorus-doped silicon for a moment. This is a very interesting system. Phosphorus-doped silicon is where you take a silicon lattice, each of these little spheres represents a silicon atom connected in this highly orderly way, and you replace a few of them with a phosphorus atom. Phosphorus goes into a silicon lattice beautifully, except it's got one spare electron that it doesn't need to bond to its companion silicons in the lattice. And that electron is the basis behind the semiconductor industry, because the control of that electron and how it allows you to modulate the flow of current through complex circuitry based on silicon is what gives silicon microelectronics its power. But this electron, when you cool the silicon crystal down, this phosphorus fifth electron stays in orbit around the phosphorus atom, and these are some artist's impressions of what the orbits look like. And in particular, this electron has a spin. And if you put this crystal into a magnetic field, the electron likes to have it spin down like this. But if you nudge it with a photon, you can lift it and flip the spin at the same time. It goes into a higher energy state. And Townes points out in his book that this high energy state has a relaxation time of 30 seconds or more, which seems like an eternity compared to most other materials, in particular ammonia, where it's a microsecond or less. So he regarded this as a prime candidate as a lasing medium. They never made it work because the transition here is not at a very favourable wavelength. However, ladies and gentlemen, I'm pleased to announce to the public for the first time tonight that myself and colleagues have found a new purpose for this electron orbiting a phosphorus atom in silicon. This is a quantum bit where the information is stored on the spin of the electron, down for a 0, up for a 1. And by the strange rules of quantum mechanics, it can be 0 and 1 simultaneously. And we have succeeded, this is not to do with lasers, we have succeeded in building a device in which a phosphorus atom that we put into the device here in Melbourne has been persuaded not yet to go into this strange superimposed state of 1 and 0, but go into a tiny circuit which allows us to deliberately program the electron, our electron made here in Melbourne, into either the spin down or the spin up state. It's a tremendous breakthrough. This is the little transistor and this microscopic image of the device we made. There is the phosphorus atom, which was actually implanted in the basement of the physics building. And here are the electrical pulses that we put into this transistor. And here's the signal coming out showing the electron is spin up. And then when we programmed it spin down, the spin up signal disappeared. So all we have to do now is put it in the spin up and down state simultaneously. And here is the quantum bit based on phosphorus doped silicon. The way is open for large-scale quantum computing. Anyway, back to the lecture. Here is the first laser. Or rather, here is the fake first laser. Over at Q's research labs, in a beautiful position on the hills looking over the Pacific Ocean in Malibu, on the outskirts of Los Angeles, Theodore Maiman stopped working on all of the projects Hughes was paying him to work on and focused in on building a laser, an optical maser. He had built a maser already in the microwave region using chromium-doped sapphires, pink rubies. And he realised that there were some energy levels that were favourable for optical emission. And so he finally, after a lot of trial and error and very careful science, he invented and got to work the first optical maser, in other words, the laser. So there's the ruby crystal. He covered the ends of it with silver to make mirrors so that light would bounce back inside the crystal. He wrapped a xenon flash lamp around it to act as the pump to lift all the electrons into the excited state, and he encased the whole thing in a highly polished aluminium cylinder, or the inside was highly polished, to reflect all the light from the flash lamp down onto the ruby, and sure enough, he got it to laze. He got stimulated emission. It was the first laser. The Hughes press office came down to take publicity photos because this made a huge splash when it was announced, front page of the newspapers. And they didn't like this. They said, that doesn't look very scientific. So he cast around and he found this very long ruby rod and this huge flash lamp which didn't work. And so the photographer, whose trademark was photographing the scientists with the apparatus in the front of their face, made it into the press, into the popular culture. And of course, people soon began ordering huge ruby rods, huge flash lamps, and couldn't understand why they didn't work. The headline headlines in the newspapers were Los Angeles man discovers science fiction death ray. And there it is. And so we see just 4 years later, obviously the Hollywood moguls are watching very carefully what's happening in the Hughes Research Lab just up the road, and here we see a gigantic flash lamp wrapped around what is undeniably a ruby rod, and James is not liking it. For dramatic impact, they've obviously just temporarily removed the cylindrical mirror which is supposed to go around it. But I thought that was remarkable, from the laboratory discovery to the cinema in only a few years. Maimon, because he wasn't in a distinguished East Coast university, wrote this up and submitted it to Physical Review Letters, which is still today one of the most prestigious physics journals. That's where you want to get your work published. The editor, Sam Goldschmidt, said, "Oh my God, not another maser paper. For God's sake, we've got too many papers on masers. No, reject it, no." But it's light, and Maimon tried and tried again, but Physical Review was hopelessly overloaded with maser papers, and so they didn't change their minds. So Maimon sent it to the British journal Nature, where it was duly published in short order in 1960 with this very modest abstract advertising and a very modest title describing the great discovery. Here are the energy levels, the ground state, the excited state, the detour, and the lasing line here represented by R1. As you cranked up the power of the flash lamp, the lasing became more and more effective, and the line narrowed and got sharper and sharper as the light went into resonance with the ruby cavity. It was a fantastic result, and he really didn't get the credit he deserved because he was on the wrong side of the US. Meanwhile, back in Bell Labs by now, intensive work is done on some of the ones that weren't successful, but they did indeed eventually invent this laser. This is the helium neon laser. Now, I can't make this work because I lost the power supply. But anyway, what I've got here is a glass tube filled with a mixture of helium and neon. And what's remarkable about this is that helium, I'm going to change colours in honour of this demonstration. Helium will gladly collide with electrons and what have you, and become excited, but the energy levels in helium are not favourable for lasing. So the idea from Bell Labs was mixing a bit of neon, in which the energy levels are favourable for lasing, and by a strange coincidence in nature, that's Mother Nature, not the journal Nature now. There's a gap in the neon energy levels that's almost exactly the same as the gap in the helium energy levels, which makes neon very favourably disposed to receiving the energy in the excited helium, having it cascade, the electrons cascade down through the neon atoms, and this energy level here has the right properties to be a laser. So let me demonstrate that for you now. It's not very good unless I do that. So here we see excitation of the, there we go. There's probably a little bit of lasing going on there by the look of it. So you can see the characteristic red colour of the helium neon laser. Now this is very simple to make and very reliable and has a very long life. There's some clever twists with the way the mirrors are positioned at the end that give this some very good attributes. And this laser quickly... I love the smell of ozone in the morning. evening. But one of the fantastic things about this laser is having these external mirrors which allow the light to resonate. And by carefully controlling these mirrors, you can squeeze all the energy of the light into a narrower and narrower strip of the electromagnetic spectrum. And that's the ability to do that is what gives lasers their enormous abilities. Now today, of course, the semiconductor laser is ubiquitous. These work very simply, simple in concept, difficult to make until the late 20th century, with a stack of different materials. their characteristics very carefully chosen so that the electrical attributes of the stack of these different materials confine electrons effectively, and by connecting a battery on the two sides of the stack, it acts like a diode, and by injecting current into the diode, it can decay down across this gap and emit laser light. And by carefully shaping the end faces of this block of material and the chemical properties of the elements in the stack, you can tune this to a number of different wavelengths, and it's extremely efficient at converting the flow of electrons into laser light. And I thought today I'd get out all my laser pointers. So I've got my green one here. This green laser pointer is actually a semiconductor laser, but it first of all starts life as a beam in the infrared, invisible, that's from a gallium aluminium arsenide quantum wave diode laser. This then passes into a neodymium-doped yttrium ortho-vanadate crystal, which fluoresces at the 1064 nanometers. And of course, you're all familiar with the idea of things that fluoresce. If I turn on my display here I've got short wavelength radiation being converted into longer wavelength radiation by the attributes of the materials that the light falls on. So this just does exactly that. These are not suitable as laser materials, I think, but you get the idea. And then it's frequency doubled by another strange crystal here, which absorbs the radiation and turns two photons into one, and in the end, a green light comes out. But you can do this not just for green, you can do it, if you change the materials a little, you can do it for blue as well. Now this one, it was fantastically expensive. This is the most number of dollars per photon you're going to see tonight. And it only just works, and the guy who sold this to me had to put in a special circuit, so he had to keep turning the laser off to stop the crystals overheating and melting. So you can see if I flip it fast, you can see it's actually a pulsed blue beam. But it is my favourite, so I'll use that for the rest of the lecture. Now, because of the remarkable efficiency of a semiconductor, thanks Steve, the semiconductor lasers and the way you can set them up, I'd like tonight, ladies and gentlemen, to reenact another thing that drew my attention to the laser when I was a young lad, namely this guy shining what was obviously a ray gun that he'd made in his laboratory. What a dream to be able to do that when I was growing up in the mid-60s, and blasting a balloon with his ray gun. Now this guy is not just any guy. This actually is Charles Towns's brother-in-law, Arthur Shorloff. He married Charles's younger sister and went on to get a Nobel Prize for good measure himself for laser spectroscopy. So I'd like tonight to reenact this demonstration, but not using whatever strange laser he was using, but a nice semiconductor laser. And this is probably the most powerful laser. What happened to the safety glasses? Okay. This laser obviously emits green light. This is not the sort of thing you want to have around the home. In a moment I'm going to remove the barrier. That'll allow the laser light to fall on the balloons. Now this is light this is 300 milliwatts, this laser. 300 milliwatts, that's not a lot, 300 milliwatts. But it's all concentrated into a tiny spot. So just as pushing on that balloon with my hand doesn't do any damage, but if I take a pin and push with the same force, the pressure is enormous and the beam will burst. The same is true of the light. So ladies and gentlemen, if you're at all sensitive to sudden noises, could I ask you to do this at this point in time, please? All I have to do is just... That's all I have to do? You'll stand. I'll do it now. Ladies and gentlemen, for the first time since 1966, but with a modern laser, let's see what happens. Ready, set, go! Oh. Well, that was very satisfying. And thanks very much to my colleague Rob Sholton, who lent me his laser and will not reveal the internet site where he ordered it from. The final thing I want to talk about is the hologram. Now, the hologram existed long before the laser. Hologram means the whole drawing. And this is the original idea that came from the Nobel Prize speech of Denis de Boer, who invented this, giving the basic idea. Imagine you've got two sources of light emitting waves. When they hit the screen over here, where you get two crests from the waves being emitted coinciding, you get a bright spot. Where you get two crests in the trough coinciding, you get a dark spot. But if you re-illuminate this screen, this image that you photograph with a bit of photographic paper just with one source of light, wherever that light hits an opening in the screen, a clear patch in the photographic emulsion, that's exactly the right point to produce light from either A or B, right? Because both A and B have a crest at that point on the screen, and so therefore whether you illuminate that point with A or B, if you look in from this side, you will see light coming as if from A or B and B. And this is the idea of the Avoidance Wavefront. We propagate light from a source by using this construction. You can imagine every point on that wavefront emits subsidiary wavefronts. And then you take the envelope of those and voila, the wavefront has progressed through space and away it goes. And once again, I thank Rob for this little animation that I pinched from his lecture notes. But in 1949, when de Boer had this idea, the only coherent light, where everything was locked in synchronization, was produced by very bright mercury lamps, and the coherence length, the length over which the light was synchronized, was only 100 microns. So you can only take photographs, holograms of very small things. But with the advent of the laser, with light locked in synchronization because of the resonances in the medium and the stimulated emission over very long distances, you could photograph large things. And the basic idea, and you'll see the examples in the foyer if you want to see holograms taken this way. You take some laser light, you reflect it onto the object you want to photograph, you split the beam so that you get another component of the light hitting straight onto the screen without hitting the object. These two sources of light, either reflected off the object or coming direct from the laser, interfere with each other, and down here you get an interference pattern. And you'll notice that every point on the object, this example is this point on its wing of the eagle here, reflects the laser light down onto the film, so every point on the object there produces a signal everywhere on the screen where it interferes with the light coming directly from the laser. So to reconstruct the image that you've recorded on the screen, you now take the reference beam, as it's called, and just use that by itself. And so using de Boer's idea, every bright spot on the photographic film that was used to record the interference pattern is just right to either be emitting light coming directly from the laser or coming from the object. And so when you look in to the photographic film, illuminated by a single laser, and move your head around, you can see different angles on the object. In other words, this is a hologram. It's not quite the whole story, because now you can tweak this arrangement so that it works just by shining not a laser but by visible white light on it in the examples in the theatre foyer, and to do that you have to sacrifice some of the three-dimensional nature of the recorded image. But the image doesn't exist here. This is an interference pattern, and if you look at this with a microscope, you don't find an image of the eagle. It's got a whole series of complicated patterns on it. But this is my attempt to show what this looks like. These are three angles of a hologram from the front cover of National Geographic in 1988. The caption was "This Fragile Earth," which is a glass model of the Earth being shattered for some reason. It makes disturbing reading. But I noticed the Australian Football League is very big on holograms, And indeed, in the paper just last week, it turns out footballers are wearing holograms strapped to their wrists, because what it does, it balances the body's energy at the ideal 7.83 hertz. I sure as hell don't know what that means. Finally, just some other applications of lasers in our society. Selected examples, I'm particularly taken with this one from when I was at school. The Apollo 11 astronauts left on the moon a series of corner reflectors. Now, a corner reflector is a device that always reflects light back the way it came. And so the basic idea here is that if you take a laser on Earth and shine it on this thing on the moon, and wait for the photons to come back again, you can measure from the travel time how far away the moon is. So the corner reflector is a very simple object, very passive, it doesn't take any power. Sorry, I need a spare hand for this. And so if I put my laser in here, you can see it comes back exactly the way it came. This is called smoke in a can. Maybe if I try a brighter one. Oh yes, you see it works beautifully for green light as well. Actually, it's not such a good demo, this one, is it? And it works very well. Okay, so the trouble with doing this is that even a laser coming out off the Earth expands to about 6 kilometres in diameter when it hits the moon. And this is a very small object. If you imagine a 6 kilometre disc of light shining down around it, only one photon in 1,000 returns to the Earth. But nevertheless, because the laser light is so sharp, these lonely photons can be counted and the travel time recorded, and you can measure the distance to the moon with a precision of just 1 millimetre, and we now find the moon is getting further away from us at a rate of 38 millimetres per year. The Russians also landed one on their Lunokhod robot vehicle, shown here on the corner of the vehicle. This thing's about the size of a large pram. It's worth noting that the technology that went into building these machines was resurrected post-Chernobyl, and a lot of these things were sent into the Chernobyl reactor to see what was going on, whereupon the intense radiation soon disabled the electronics, and most of them are still in there apparently. Also, of great import to those of us who got stranded in Europe because of the Icelandic volcanic crisis, you can use lasers in the way you can use radio waves to bounce off things and measure how far away they are, LIDAR instead of radar, and indeed this is from the BBC website a few months ago showing the volcanic plume over Europe measured by bouncing lasers from space reflecting off the ash particles and recording the three-dimensional structure of the plume. The high energy lasers are now shaping up all around the Earth, and these